Back in Europe, we have our own exciting active volcanoes. Mount Etna lies on the island of Sicily. The snowy peak is over 3,000 meters above sea level. As we approach Etna, we can see that there are several little cones on the flanks of the volcano, and up at the top there are 4 craters. They are almost continuously active, emitting hot volcanic gases and ash. With less snow on the ground, you can see ash among the lava flows and occasionally hear the explosive escape of gas or a volcanic bomb. This bomb is over 1 meter across and was thrown more than 2 kilometers from the southeast crater since we were last here. The bomb is elongated like this because it was still hot, plastic and spinning when it was thrown from the crater. Another ash cone, the northeast crater, with RR lava in the foreground. There are basically 2 lava flow types, and we give them Hawaiian names, Pahoehoe and RR. The type of flow depends on the temperature, the gas content, and the rate of flow of the lava. This ropey structure is called Pahoehoe, and the more broken up rubbly texture is RR, which is almost impossible to walk on. Sharp, jagged, uneroded lava flows like this are just a year or 2 old. All that is left of a small hostel which suffered badly in the 1983 and 1985 eruptions. The building was torn apart as the ground opened and the lava was erupted through it. With over 40 major eruptions having occurred in the last 25 years, Etna is one of the world's most active volcanoes. Even when relatively quiet, the summit craters are full of gas, mainly carbon dioxide, sulfur dioxide and steam. And when eruptions do occur at the summit, they're usually mostly ash, although sometimes magma overflows out of the crater, building up the cone. Eruptions are not always confined to the summit craters, though. A lot of the magma, which is intruded from depth, comes up in the form of dikes. When these hit the surface, they give rise to what we call fissure eruptions. Here's one. A dike cuts through the horizontal layers of eroded volcanic rocks and soils, and at the top feeds a lava flow. There are several of these dikes very well exposed in the large scarp face on the east of Etna. There is a huge collapse feature here. It's about 1 kilometer deep and 5 kilometers wide. The side of the volcano has just disappeared. Inside this arid valley, the Valle del Bove, there are cinder cones and lava flows. We will return here later. But first, we must join the OU Volcano Geophysics group nearer the summit.
.9163. 0.9062, 0.9165,
1.4360.
Okay, Helen.
This group is using the oldest and most precise technique for measuring altitude differences, levelling. John Murray.
When you begin levelling, you start from a station of known height and progress in stages to a second station.
Okay.
The level is a telescope which can be precisely aligned to the horizontal. It sights onto a leveling staff, which is essentially a large ruler. The staff has to be held exactly vertically, and in order to do this, Helen has to constantly check to make sure that the bubble is in the center of the circle. Using the barcode, the instrument can sense where it's pointing to on the staff with an accuracy of about 1/10 of a millimeter.
2.6841. 2.6841 again. 2.6839. 2.6843.
2.6841.
A simple subtraction sum gives the height difference between the two stations as 1.9578 meters, and so on to the next one. Measuring height differences between as many temporary stations as you need to bridge the gaps between the fixed stations in your network.
0.9165.
The entire leveling network on Etna consists of about 300 stations, and the distance leveled through all the branches of the network totals 26 kilometers. The precision of the method gives altitudes which are accurate to about 1/1,000,000th of the distance covered. This means that over a distance of about 10 kilometers, we don't expect errors greater than about 10 millimeters. Regular monitoring is essential to see the slight changes in elevation, usually just a few centimeters, which act as the prelude to an eruption. Along with the microgravity work, these ground deformation studies help us to find out where the magma is and to distinguish two different kinds of eruption on Etna, those involving the summit conduits and those which break out on the flanks. Over terrain like this, it's impossible to use the leveling technique, so we use a different method of obtaining relative heights. First, we locate the fixed station, which consists of a survey nail implanted into solid rock, and set the instrument on a tripod vertically above it. And we measure the height of the optical axis of the theodolite above the fixed station.
1.370.
Okay.
A special target is placed round the objective glass. Check that the LED display is working properly.
Okay, Helen.
We're all set up this end and ready to read vertical angles. Are you?
Yes, we're ready to, over.
Okay, reading on to you now, over.
Okay, over.
Across the crater, Helen has set up her theodolite in exactly the same way.
Okay, 266, 53, 20.
All right.
Okay, 266, 53, 30.
Right.
Vertical angles are measured from both ends of the line at the same time. This eliminates any effects of refraction due to differences in the refractive index of the air.
93, 07, 07.
Face right. 86 degrees. 53 minutes. 20 seconds. Okay, Helen, we've finished reading on to you. Are you finished yet?
Yes, we finished too, over. Okay, can you put your prisms on when you're ready? Over.
Okay, over.
When we have finished measuring the vertical angles, Helen replaces her theodolite with a reflecting prism.
Okay, John, the prism is in position now, over.
Okay, Helen, we're shooting onto you now.
My instrument then sends a pulse of infrared light and automatically measures the return time.
Face right distances first, okay?
The distance is given to an accuracy of a few millimeters over 1 kilometer.
265.743. Okay, read your first temperature now.
Okay. 1.2 degrees. Pressure 788.
Our temperature is plus 0.3. And the pressure is 780.
These values affect the velocity of the infrared beam and the distance we obtain.
265.743. Okay, face left distances now. Face left.
Using simple trigonometry,
Vertical.
we can calculate the horizontal and vertical distance between stations. The technique you've just seen is called triangulateration.
Okay, Helen, we've got all 6 distances now. So if you can pack up and move down to IC11, we'll stay put here. Over. So, having made a large number of these triangulateration measurements, what we end up with is the precise positions of a large number of points over the entire volcano. So when we come back next time and remeasure these points, we can see how the land has moved, so we can tell if faults have opened or if land has dropped relative to other parts of the volcano. And what we find frequently, particularly on the eastern flank, is that part of the volcano has slipped down, so that you have a situation where one part slips down like this relative to the other.
Now, let us return to gravity measurements, both static and dynamic, and the contribution they make to our knowledge of the movement of magma beneath Etna. We begin 50 kilometers west of this point, in the town of Centuripe. It is on a sedimentary basement, and there in the distance you can see Etna. This is an excellent place for a base or reference station because we are well away from any effects of the volcano. But there's another reason for coming to Centuripe. It contains an absolute gravity station set up in the basement of a school. This part of the apparatus is the laser generator. Another complex piece of the setup is concerned with receiving and transmitting the laser beams and redirecting them into a cylinder firmly anchored onto the floor and supported by granite scaffolding. This is the absolute gravity meter. Inside the cylinder, and shielded by a wire mesh from any magnetic effects, there is a mass. Beneath it, a spring is being tensioned. When released, it will throw the mass upwards, and then the mass will fall back under the force of gravity. On its way up and down, reflectors on the mass will intercept laser beams and reflect them back. Here in its rest position, you can just make out the reflecting prisms. And here, see the laser beam. Caught mid-flight, this frozen frame shows the mass during its descent. The computer calculates how long it takes the laser beam to return, and this, of course, depends on where the mass is at that time. An instant later, the mass has moved down a bit, and the computer recalculates its new position and time. Now let's see an experiment being done.
Okay.
Our Italian colleagues are measuring the absolute value of gravity as part of an international project to see how the geoid changes.
Pronto?
The computer does millions of calculations as the mass rises and falls, and measures the acceleration on the mass, that is, the acceleration due to gravity. But the value of gravity changes here, even in this relatively stable vault, and that is because of the Earth tides. So, once we have an estimate for the value of g, we need to add or subtract the tidal component. Then we end up with an absolute value of gravity for this point.
1, 7744.
This station is very useful for our gravity work on Etna. If we make measurements here and at other absolute stations with our relative gravity meters, we can actually calculate the real or absolute value of gravity at each of our stations on the volcano. Normally, we wouldn't expect the absolute value of gravity to change after we'd made the tidal correction. If it does, it'll be due to the whole island rising or sinking due to isostasy.
Getting there?
Yep, I'm there. It's about... Whether that is happening or not doesn't actually matter for our more localized measurements of gravity, but it does matter in that it will be related to the magmatic processes which drive the volcano. We are actually using gravity on 3 scales here. We have the absolute gravity measurements, which give us a global or tectonic view of very deep sources within the volcano. We use static gravity measurements to build up a 3D model for the structure of the volcano. And then we home in on the very fine detail provided by microgravity measurements, which relate to small variations within the plumbing system itself.
Yeah, that's a good one.
Yep.
In order to map out the broad gravity signature of Etna, we need to set up a few hundred static gravity stations all over the volcano. This is just one of them, on top of a 1,200-meter drop into the Valle del Bove. It's freezing cold up here, but the instrument's nice and warm, connected to a battery in my backpack. Elevation control isn't quite so important in this case as it is for dynamic monitoring of gravity, because we're looking for anomalies of several milligals rather than changes of just a few microgals. That's why we use this altimeter for making the elevation measurements. It's good to a meter or so, and it simply works on changing air pressure with elevation. Although we're quite close to the summit of Etna, we find almost no gravity anomaly here because there's hardly any density contrast beneath the ground. Let's see what happens when we descend into the Valle del Bove. Just a reminder, that a large proportion of the volcanic output is ash. These scree slopes are quite fast to climb down, but almost impossible to climb up. This is about the only useful place for a gravity station on the way down. The relatively stable platform is part of some dikes which have been intruded into rocks that have since weathered away. As an intrusion of molten rock beneath the surface, these dikes take anything from a few days to a few weeks to freeze. The bigger, thicker dikes that take longer to cool sometimes form these columnar joints. Most of the dikes here run parallel to the cliff wall, and as each of these dikes has intruded, so the cliff has grown sideways to accommodate them. So this part of Etna is actually moving, gradually to the east, downslope. These dikes have a complex relationship with the Valley del Bove. They make the cliff wall strong enough to exist, but the wall collapses when it gets pushed out sideways by new dike intrusions, causing huge debris flows. As we've descended, gravity has changed. Here, it is higher than it was at our previous station, Station 31, 600 metres above. "600 metres below is our next gravity station. A ruined farmhouse called Menza. Here at Menza, we've chosen the well to be the stable platform for our gravity measurements. Once we've made corrections, the latitude, free air, bouquet and terrain corrections, we can make a map of gravity for the whole of this region. Once we've done that, we'll probably find that the anomaly is 10 milligals or so at its largest, and from the amplitude and the wavelength of the anomaly, we'll be able to work out the subsurface structure of this volcano in terms of density contrasts. But to look at magmatic processes and detect the intrusion or indeed the drainage of magma within the volcano, we need the higher resolution provided by microgravity. Before we can make our dynamic gravity survey, we need to set up a base station. We'll do this in a town called Nicolosi, on the southern flank of the volcano. It's actually part of the Italian gravity network, so our whole survey can be tied into the national grid this way. Because this is a dynamic survey, we need to make the tidal correction. We need to come back at the end of the day to this base station so that we can correct for any instrumental problems that we've had. This one is 3350. Have you done a tidal correction? Ideally, of course, we'd like to go back to Centuripe, the absolute gravity station, but that's too far away. And we make do with a nearer reference station, where we assume gravity remains constant. Of course, we can always check that by comparison with our measurement at Centuripe. This is the first of the field stations. We call this station Shistanatsa. That's the name of the explosion crater formed in 1723, right next to it. Earthquake passing. Did you clamp your meter for that?
No.
It's pretty good reading.
Fast. Keep up with it.
Although we're going for very high precision measurements here, there are lots of factors conspiring against us. Every time the volcano explodes, there's a vibration, and the instrument takes some time to settle down. When the wind blows, the same thing happens. And of course, when a tourist bus goes past, it's even worse.
Remember?
Yes?
2873.
We stayed at each station, just as long as necessary to get 3 readings, where we could see that the mass in the meter was exactly in the null position. Then we move on. Typically, on a survey day, we do 10 to 15 gravity stations, although it does depend a lot on the weather and the distance between the stations.
So where do we go next then?
Station 6.
Okay, station 6.
Station 6 is closer to the summit by about 1,000 metres. In 1989, it was just missed by a lava flow, the Black River you can see in the background. About 10 milligauss left here, I think.
Cool. Very flowy.
Yeah. My needle's wobbling around all over the place.
Yeah. Remember when we were set up with the EDM here and it all blew over?
Yeah. It's not quite that bad today. What's your number?
2858.
Yep.
576.
At 13:15. 293. Despite the wind, we work up the results. That way we can choose our stations as we go along, following any interesting trend in the readings. Once more, we're searching for a rock with a nail in it that's our station G24. Since we last came here, microgravity has increased. We've been following a trend we've been seeing at the last 2 stations. Stations to the east and west haven't changed much, so we're seeing a linear feature which looks like a dike. Back at G24, Jeff is measuring gravity now. Finding flat areas on stable volcanic rocks is not easy, and here we have to read the gravity meters one at a time.
On to number 2792.986. That should have been 2791. It's right at the end of the range.
This is going to be our last field station of the day, right on the edge of the central summit crater. Jeff and I have gone off to measure 2 more stations east and west of G24 before climbing the 300 meters to our crater top station. As night falls, the air begins to clear. Perhaps we'll get a good view into the crater. About 200 meters down, there's a vent erupting every few seconds. It's quite difficult making the measurement here because the ground's vibrating with these eruptions, and also because it's very tempting to keep looking across and seeing what the volcano is actually doing. The lava is rather higher in this crater than it was last time we were here, and so, not surprisingly, the value of gravity at this station has increased too. What we think's going on is a dike has been intruded beneath the surface since we were here 6 months ago. You can see it runs parallel to a line of fissures formed in the 1989 eruption. It may well be that gravity increases were caused by magma filling the fissures beneath the surface. What will happen to this dike in the future, we'll have to see. It may cause fissures to open up on the volcano's flanks and may even feed a flank fissure eruption. Only time will tell. 2 months later, the eruption occurred at the weakest point, halfway down into the Valle del Bove, near what was Station 32. This is the position of the new lava flow, showing its relationship to the dike we saw from the gravity data, and the cliffs dropping down into the Valle del Bove. What happened looks something like this. Rivers of molten rock flow from the fissure in the wall on the Valle del Bove and fall down over the cliffs. The flow extends several kilometers into the Valle del Bove and goes around the ruined farmhouse we saw earlier. Every volcano presents different problems for the geophysicist, even if it's just the logistics of getting as close as possible to the centre of activity, because that's where the gravity changes are going to be largest. When climbing to the highest station on Arenal in Costa Rica, one is only too aware that some of these boulders have been thrown out of the volcano within the last few hours. Arenal erupts about 12 times a day, but now and then the vent gets blocked. When this happens, the next eruption is rather more violent.